Welcome everybody. We are happy to have today with us Professor Tushar Prabhu to deliver a lecture under the IIA-50 commemorative lecture series. Professor Prabhu has had a long career at IIA. After graduating with an MSc degree in physics from IIT Bombay, he had joined Professor Venu Bapu as a research student in 1973. Later, he had applied for an advertised position and joined as research associate in 1975 and retired as a senior professor in 2014. Prabhu completed his PhD study on central regions of Sarsic Pastoriza galaxies in 1979, and during his career, he has worked on galaxies in the local universe, as well as galactic novae and extragalactic supernovae, mostly using optical imaging and spectroscopic techniques with the telescopes at Vibio, Cavallur. He has over 100 research publications in refereed journals and guided 5 students towards their PhD degrees. During his early career, Prabhu was involved with procurement and testing spectrographs and development of digital data reduction software for optical spectroscopy. Now, during the later part of his career, he was involved with the identification and characterization of high altitude site at Hanle and development of Indian Astronomical Observatory with a 2-meter Himalayan Chandra telescope, as well as high altitude gamma ray astronomy array. He has also had a long association with the development of 3.6-meter Devastal optical telescope, ARIES Nainital, and today he will tell us about 4 decades of development of spectrographs he had witnessed at IIA for use with telescopes at Venubapu Observatory, Cavallur, and Indian Astronomical Observatory, Hanle. Prabhu has served on the editorial boards of Journal of Astrophysics and Astronomy, Indian Academy of Sciences, and Bulletin of Astronomical Society of India. He held responsible positions at IIA at various times, which include project manager of 2-meter telescope at Hanle, professor in charge of IAO and CREST, and also served as Dean of IIA. It is with great pleasure, on behalf of the IIA-50 Organizing Committee, I welcome Professor Prabhu to deliver his talk, Development of Astronomical Spectroscopy at IIA. Professor Prabhu.
Thank you, Aruna, for your kind words and also for giving me an opportunity to talk in this series. Can you hear me well?
Yes, we can hear you.
Yeah, okay. Are you able to share my presentation? I'm sorry, I could not connect from here.
Yeah, Anupama is sharing your presentation.
Are you seeing it?
I can't see it
Yet.
Can you see it now? Now
Not
that I presented, not yet?
Not yet.
Okay, let me try sharing once again because I think I was not the presenter at that time. Do you see now?
Not. Yes.
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 Okay.
Make it full screen. You could make it full screen. Yes.
You opening from the drive itself.
No. Yeah.
Actually, see, I did not realize that it has become too heavy with pictures.
No, wait a minute. Sorry. Let me stop sharing first. And I will go to
obsolete, and solar spectroscopy was taken up routinely. And we come to the next slide, which is from the IIA website history, where Bapu has written under subsection Stellar Physics at Kodaikanal that for studies of physical properties of stars, the observatory had limited instrumental resources. Nevertheless, he Evershed observed ultraviolet tail of comet Daniel and Venus, Nova Aquilae, high dispersion spectra of Sirius, and so on. And you may just wonder, comet Daniel and Venus, what do they have to do with stellar physics? And it appears that with all that emphasis on solar physics for such a long time, people had to find out the right name for rest of astronomy. And he used the word stellar physics. And in this particular series, I heard Rajesh Kochar talk of nighttime astronomy. Okay, so all astronomy other than sun is nighttime astronomy. And what did Bapu do for nighttime astronomy? The next slide. There are 6-inch and 8-inch telescopes already moved from Madras to Kodaikanal, but there was also a much bigger telescope, a 20-inch telescope known as Bhavnagar telescope after the benefactor Maharaja Takht Singh Ji. You can get its history in Kameshwara Vettel Current Science article, but particularly what interests us is that soon after Bapu came to Kodaikanal in 1960 as director, he built a spectrograph for the telescope that formed the basis of several studies of stellar spectroscopy right at Kodaikanal, including comet IIA-50. I'll mention this again later. And the next slide. So along with it, Bapu developed a Kavalur Observatory, identified the site, and ordered a 1-meter telescope. And by 1972, it was installed. And my reminiscences here are in parallel with this, how my path converged to Kavalur. So in the next slide, I come to my own personal reminiscences. 1965, Ikia Seki again. My mother worked all of us children to watch this fabulous tail. We couldn't see the head because it was behind some buildings, but the tail was extending everywhere, and I got interested in looking up into the sky, identify constellations, and so on. And I wanted to study astronomy for future, so I find out what to do. I found some spherical astronomy in mathematics somewhere, and people told me that is not the thing. You have to do physics to do astronomy. So I moved to where I can major in physics to Pune. And from there, I started writing letters to whatever addresses I found. I thought I could do MSc in Osmania University because they had a 1.2-meter telescope around that time, 1968. And so I got the addresses of Abhyankar, head of the department, and Karandikar, director of observatory. I was more interested in observatory, so I wrote to Karandikar asking what should I do, and he never replied. And then I decided to go to TIFR because I knew there was some astronomy going on there. And I met Professor Vardya. He told me, don't go to Osmania, study some physics first. And IIT Bombay is probably the best place. You finish your MSc and then come and see me. So while at IIT Bombay, one of my teachers of X-rays and crystallography, Leela Rao, asked me, what would you like to do after your MSc? I said my first interest is astronomy, particularly optical astronomy. And Osmania, I'm not sure of going to, but TIFR, I'm not sure they will take me into. But TIFR doesn't have optical astronomy also, so I don't know what to do. So she said she has heard of one Venu Bapu at Kodaikanal. He is the director of an observatory. That may be the good place for you. That is the first time I heard of Venu Bapu, though I should have known before because when I wrote to various places, I find that I wrote to the secretary of International Astronomical Union as well, and their vice president M.K. Venu Bapu was there on the letterhead. In the next slide, we'll come back to Kavalur, and when soon after she told me about Venu Bapu and Kodaikanal, there was a announcement in the on the notice board of physics department in IIT Bombay that there is going to be a workshop in astronomical spectroscopy at Kodaikanal for students of astronomy and astrophysics, research students of astronomy and astrophysics, and teachers of physics. And contact person was J.C. Bhattacharya. So I wrote to him that I am neither a research student nor a teacher, but I want to take up astronomy as my career, and I am just an MSc student right now. If I am eligible to attend, I would be interested. And if if you select me, I would like to have some support, financial support for me to come and attend. There was no news from him until December beginning. I got a telegram saying selected for the winter school. Uh, uh, Come and join by 26th of December. So I didn't know what to do. I just bought a ticket and whatever money I had and came to Kodaikanal and found that everything was taken care of. There was accommodation, food, and lectures arranged. So during that period, I met Professor Abhyankar also first time. So I asked him, what should I do to take up a career in astronomy? He said he is extremely dissatisfied with physics students. So if I want to do astronomy, I should do MSc Astronomy Astrophysics first. So then I asked Bhattacharya, what should I do? He said, you should talk to Bapu. Bapu was an imposing personality. I couldn't talk to him immediately. And then after 2 weeks in Kodaikanal, we were taken to Kavalur. And at Kavalur, I saw the 40-inch telescope for the first time, and that energized me and gave me sufficient strength to talk to Bapu. And I thought I will show you something here, which was at the Cassegrain of the 1 meter telescope. So there is an instrument which is looking like this with a bend here. And one of the professors from the university who was attending, he said, oh, so something has hit and bent this thing. You should straighten it out. Bapu said, no, there is a prism here, and this gives me spectra of the entire sky. The spectra look like this. So these were the first spectra I had seen with the 40-inch telescope. And sometime we removed this, Bapu removed this and put a eyepiece turret at the 40-inch telescope, and all of us had the opportunity of viewing through the 40-inch telescope, such a big telescope, and things like Omega Centauri showed thousands of stars. And while people were lined up to see, I approached Bapu and told him that I want to uh, join this institute for my PhD if possible. He said, okay, let us talk, and took me to the catwalk outside. He said, now tell me, beginning from your primary school, everything you have done, all your successes, all your failures, up to MSc. And I went on telling him all my successes and also my failures. And then he suddenly said, let us move down to my office. So we went down. Actually, he said it's cold here because he saw that I was shivering. And I continued to shiver in the room, but still completed my confession. And at the end, he said, okay, you write to me after you finish your MSc and send me your marks cards. So next slide shows the letter he sent to me, an offer letter. He told me to come and join. He gave me very little time. I missed the date on top here to June 25th, asking me to join before the middle of July. With the letter took a week to reach me, and then the postscript here that middle of July I should come to Kavalur and see him first. So I went to Kavalur, and he was there in Kavalur. I went around 20th or so, and so he told me to settle down in one of the rooms shown to me, and dormitories rather. There were no rooms, and then after lunch he took me to the telescope and began to teach me immediately how to operate the telescope. So the 40-inch telescope, and then at night he showed me how to use the spectrograph. And the next slide shows, I don't have the picture of the spectrograph, but in the next slide, okay, before that, he also told me that he wants me to do spectroscopy of galaxies for my PhD. But until then, until I start that, I should do some projects. Since there is no coursework, I should do projects in stellar spectroscopy. And these were the actually kind of spectra which he called microspectra obtained with a small prism. I thought of showing this because there was a extragalactic spectrum, the QSOs, Bapu and Parthsarthi. Parthsarthi was my senior and was a research associate there at that time, along with another research associate, Rajmohan. Two of them were research associates, and there were some research assistants and senior research assistants. So so, but I didn't have to do this. He gave me the spectrograph, the so-called Bhavnagar spectrograph. And next slide shows you the appearance, I mean, the general concept of that. I didn't have a picture of the spectrograph. There's a conventional spectrograph with a collimator, lens collimator, and a lens camera. And this gave me an opportunity of learning about spectrographs in general. I had to, there are no textbooks for astronomical techniques. So I had to go back to my physics books to understand diffraction grating, the grating equation, understand cos alpha, cos beta, and so on. And also the detector was photographic emulsion. We had to do our own cutting, whether it is plate or film, and developing, fixing. I put in whatever order came to my mind. Sometime we did some hypersensitizing. We had to do intensity calibration and measure the position with a Abbe comparator, wavelength calibration, and so on, microdensitometry. So this was my basic laboratory course for the PhD program, and Bapu gave me one project straight away. It's the same night we started observing. So the next slide shows that project of on a shell spectrum of Pleione. It is 28 Tauri, the seventh sister in the Pleiades, and the it undergoes periodic outburst, normally a B emission line star of B type, but sometimes it ejects some material and it forms a shell around it. So it was in shell phase, and so Bapu taught me how to take spectrum, how to measure lines, and how to estimate electron density from how many Balmer lines you can see, and so on. And effectively, he did most of this work, and his name appears as second author. It was presented at ASI meeting 1974. He told me to take another project from Parth Sarthi. And Parth Sarthi suggested the Delta Library. And here I am the only author because Parth Sarthi taught me everything of what to do, and I did all the work. So at that time, it didn't occur to me that I should ask him, shall I put your name as co-author? And Rajamohan was also another person who helped me a lot to understand how exactly I should decide on the epochs of observation so that I have a uniform coverage of the entire orbit. And both these were never published. I thought that I may be able to publish this. I left some blank here, and I was searching for my old lab book, where on the front page I had quoted Firag Gorakhpuri, "अब भी कोई बना ले तो बिगड़ी नहीं है बात." But maybe it is too late now, so it doesn't matter if I don't find it. So I moved forward. So the next one shows the what I had to learn about the photographic emulsion. It is extremely nonlinear. So what we call optical density is some function, mostly logarithm of the transmittivity. So how much darkening is there in photographic plate, and log of exposure could be if intensity is varying intensity with the exposure time constant, or in laboratory we sometimes varied the exposure time, like in the calibration spectrograph, the rotating sector. So constant intensity, but varying exposure time gives you the exposure H as it varies. So you draw a calibration curve like this. Here it will look a linear portion, but if you take the plot the slopes, it varies quite a bit even doing in the linear portion here. So the accuracy and the measurements points are also, measurement accuracies could vary because this varies from batch to batch or on the same plate, and how you develop and so on. So it was not such a good detector for a high accuracy calibration. And most of what I learned was by helping the thesis reductions of Rajamohan in 1970 for a few months. I worked with him. And before that, of course, he had tried to, Bapu had asked him to teach me how to do the tracings of the density from the spectrometer using a microphotometer or microdensitometer. The words used were used to vary. So there was one in Kodaikanal which was very, very old and not working well. Rajmohan used to get frustrated working almost whole night, and I used to be bored sitting there watching him. And but finally, finally, there was a Carl Zeiss microdensitometer procured in 1974, with which digitization became much easier. And so it would give a tracing, analog tracing, Then we sit down and measure on that with a scale and determine how much is the deflection. And there was a microcomputer of ACIL with a 4K memory. We said 4K at that time, so I don't know whether it was 4 kilobits or 4 kilobytes, but it was very, very limited memory. But we managed to do some amount of reduction there. Some people wrote programs, some people ran it. I fed the data. So I was data entry operator at that time. Okay, so the next slide shows other developments which are taking place at that time. So Bapu made a Cassegrain object acquisition and offset guiding arrangement, which is shown here. I will mention it again later. And there is a series of spectrographs he was building and testing. A littrospectrograph for the Cassegrain and Eshel at Cassegrain, and Coude spectrographs A and B, and Coude A both had the same collimator which was sitting in the ground floor of the telescope building, and uh, and one of them, Coude A, had a Schmidt camera which has a curved focal plane, so we had to bend the plate, which was very difficult to do. And Coude B was a long focus camera, so the focal plane was flat. And a lot of observations were done by Coude B by people, but its limit was very limited: Canopus, Polaris, brightest stars. And Coude A was anyway dismantled, and it was converted to Schmidt telescope later, which Rajmohan used to find all those asteroids, including Ramanuja and Bhattacharya, Menon, and so on. And the Coude Eshel spectrograph. So this data from this Rajmohan used for his thesis, and the Carl Zeiss microdensitometer was procured, which helped us to digitize. And Bapu also developed a computer-controlled photoelectric spectrum scanner with the help of ECIL. The TD-SITWL computer was procured for that, but Rajmohan could use it, I could use it to learn Fortran 2 and so on, until this instrument was ready. After the instrument was ready, it was dedicated to the instrument. Because its memory being limited, it was not uh, able to do any multitasking. So we again didn't have any further luxury of using computers for some time after that. So the next slide shows the Coude Eshel spectrograph on a table when it was under maintenance. I found this picture in Malik's uh, article in Current Science. For 25 years of astronomy at Indian Institute of Astrophysics. And this entire 25 years of astronomy has been nighttime astronomy, if I may remark. This when I took this picture from that article, I just remembered also that the only courses, graduate school courses I have had are due to Dipankar Malik in Kodaikanal Observatory Library on stellar structure and evolution and on astrophysics of gaseous nebulae. The first edition of this Osterbrock's book was not yet out, but Malik had learnt it directly from Osterbrock, and he had proofread this book already, and he taught us exactly the chapters from this. And I say us, I mean, I was one student, and Sushma had joined next year. But apart from two students, all the rest of assistants, associates, many people who had joined during that time, so they had all come from physics background, so they also attended these classes. And this was very useful for me for my further studies of spectroscopy of whichever objects, particularly the emission line spectroscopy, which I specialized in later. Okay, the next slide shows. Okay, before I start on this, I should add something more. So after Malik's courses were over, I just mentioned that a lot of people were coming and joining with physics background. There were many advertisements coming in for assistant positions and associate positions, fellows positions, and so on. So there was one advertisement for associate professor, research associate, which was appeared just suitable for me. It required MSc with some research experience. So I wanted to apply, and I wondered whether I should just apply or whether I should ask my supervisor. So I finally waited for a time when Bapu had gone to Kaulur and wrote him a letter, since I couldn't speak to him directly. So when he came back from Kavalur, he just looked at me and said, apply. I applied, and same time Venkat Krishnan had also applied. So both of us got that position of research associate in August 1975. And in end of August, there was a newspaper report. There was a naked eye nova in Cygnus. 30th of August was the peak, and it must have been around that time or 1st of September. And skies were cloudy uh, in Kodaikanal. We couldn't look at it, but Bapu said, go immediately to Kaulur and start observing. And I went to Kaulur. Kaulur was also cloudy, and waited for some time. It cleared and looked up. Cygnus is a big constellation. I compared with Northern Star Atlas. I couldn't locate the uh, nova. And then we had a astrograph there, which is called M camera, because Mohin had gone to Bombay and got it cleared through customs and brought it there. And he had also learned how to use it by mounting it on top of the 15-inch telescope and using 15-inch telescope as a guide telescope. And so we took a picture of a Cygnus region, and both of us looked and couldn't locate. But then we got a telegram from Bapu providing coordinates. Then I pointed the 40-inch telescope, and by September 20th or so, I started observing, monitoring this nova. This was nothing to do with my thesis, and already I had two projects which Bapu had told me about. But there's excitement of observations, and there was excitement of getting a new job, whether PhD or not. So I rushed to observe this. And the next one shows what I got out of it. There's quite a bit I published in this paper, but in particular, I could convert the H alpha profiles into the velocity axis here and relative intensity. And this was done without the computer in Kaulur because it was no longer available to us. And getting the microdensitometer tracing and measuring the deflection and drawing a calibration curve, reading out, and so on. It was very laborious. But by then, I started observing whatever novae which occurred since then, and the photoelectric spectrum scanner was ready soon, and it's so much easier to get that. But of course, counts here. I had not yet learned to do spectrophotometry, and mostly that was one reason. And other reason is most of the time, as a research student, I used to get entire rainy season as my time on 40-inch. So I had to observe through clouds or in between clouds and so on. And another interesting object I observed next was again in the rainy season. The next slide, it was with Shailaja, an outburst of U Scorpii. Shailaja was with the electronics section, and one day Bapu called me and said she wants to start observational astronomy and to go to Kaulur and teach her. And 79 was the year I was trying to complete my thesis on galaxies. So I just tried to explain my objection. But he didn't listen. He said, once you have learned something, it is your duty to teach others. And then suddenly I learned about the U Scorpii outburst. And whether thesis or no thesis, it was my habit to rush to Kaulur whenever there was a nova. So I told her to come along, we'll observe this. So we got some spectra, and there are not many observations around the world at that time. And so we got some photographic spectrum through the clouds, and again through clouds, some photoelectric scanner also, very noisy. But this is the first attempt to convert something into flux scale on this. Okay, in the next slide, so we'll move forward to my attempt to study galaxies. Because Bapu was hell-bent on my observing galaxies for my thesis, and particularly spectroscopy. He says spectra, I say spectra. And Bhavnagar spectrograph slit was very, very poor in reflectivity. I could never see any galaxy there. But using this acquisition and guiding unit, where you adjust the position of the eyepiece such that the cross wires coincide with the center of slit, and then move it away so that the object will be exactly on the slit. And tried that. Even that was quite difficult because of reproducibility and so on. And I said I cannot do it. Then one day he called me and showed me a spectrum Rajmohan has taken. So he had just removed the slit of the Bhavnagar spectrograph and pointed it to the Seyfert galaxy. I forgot, it was NGC 4151 probably, one of the brightest Seyfert galaxy, and got a spectrum. I said, fine. So it was very innovative. But what would I do with such a spectrum whereas everyone has been observing at much higher resolution with much better telescopes? So Bapu said he'll build one more spectrograph. He called it a nebula spectrograph. In those days, nebula spectrograph is meant for the use on extended objects where the reduction from slit to the focal plane is high due to a short focal length camera compared to the collimator. Collimator focal length by camera focal length is high. So with this nebula spectrograph, the slit was a reflecting slit, so I could see the galaxies on the slit. And the collimator was reflecting, so the efficiency is much higher. But the Schmidt camera which he used, the same Schmidt camera which used the 103 AE film. If you remember the earlier slide where of the dip in the efficiency. So he said, okay, forget it, and got a focal lens camera, and imaging lens. Right? That's what I used for some spectroscopy after that. And of course, this was used by others also by using a higher uh, number of lines grating to get higher dispersion, and also 10-inch and 20-inch focal length cameras, so that much higher dispersions were possible in this, though it was a nebular spectrograph. Sometime we stopped the word nebula and started calling it Cassegrain image tube spectrograph because it became a multi-purpose spectrograph. But I couldn't really do much towards my thesis with this. I went for just imaging again. But next slide shows a little bit I could manage to do with this spectrograph. So for some galaxies, I could get spectra the sufficient accuracy to get the radial velocities, and they were all in different dispersions depending on the how faint they were. And so this was my first paper on galaxies in Kodaikanal Observatory Bulletin. I learned a lot during this period that if you mount the grating with blaze angle away from camera, this is the opposite of what people thought, that blaze angle should look towards camera because the normally the reflection looks in that direction. But blazed, if you do this, Hollands and Reisema, they were actually master students at that time and they wrote the paper. They showed that the efficiency of spectrography is better this way. And I also learned about the curvature of the slit. Image of the slit in the focal plane is curved. So we have generally the comparisons spectra on either sides from which we determine the wavelength scale, but it may not apply exactly in the center because the center may be slightly shifted. And I gave the reference of Minkowski, but Bapu told me, go to library and open Kodaikanal Observatory Bulletin, Volume 2, and look for Walker's article. And that was much more detailed than Minkowski's. Okay. And continuing to the next slide. So I did manage to do something. So Bapu went on talking of wide slit spectroscopy because the at the time of eclipse, people did not use slit. The one edge of the lunar limb itself was edge of a slit, and as the rest of it depended on corona's brightness. So it was like a wide slit spectroscopy. You had all these lines in a curved image, and similar uh, techniques was applied by others for nebulae also. And Bapu was asking me, why don't you do it for galaxies? So the central emission line regions I managed to get for a few galaxies, like NJC 50 to 36. So this is an H alpha image directly imaged with a H alpha filter, and this is a spectroscopic image. The contours are shown here, H alpha and nitrogen 2 line. And I managed to do this, but I again grumbled that the velocity field in this galaxy distorts this. So I won't have position to position match. It will be difficult for me to know unless I know the velocity field and correct it back for it. Then I suddenly wondered, why don't I use this to determine the velocity field itself? And I referred to some book in library and found that the two components of velocity affect these contours in a way that one component causes a shear, which does not change the area of the contour under the contour, and whereas another component will cause compression depending on direction or dispersion. So that compression, where it is expansion is also called compression. That compression is a term. So it changes the area. So if I see how the isototal area varies, and square root of area or square root of area by pi was called the equivalent radius. So that the equivalent radius in spectroscopic image and the direct photographic image, I will have the velocity term. This beta contains the v by c and the dispersion and so on. So I will be able to determine the velocity curve itself. So it was fun doing it, but I never published it because I didn't know how accurate this would be. But this was the only spectroscopic result in my thesis. Okay, following, but subsequent to thesis, as you see in the next slide, I moved away from galaxies for some time and started uh, observing spectra of supernovae. And I did not spend as much effort in that as with the Nova Cygni 1975. I just published spectra with the transmittance just as this because it was too laborious to convert them to intensity. But eventually, the things became more comfortable. And yeah, before going to that, I'll tell you one more technique which I used due to GSD Babu. So he made an attachment to the Cassegrain focus where you could hold a diffraction grating, transmission grating just above the photographic plate and get a spectrum. And closer you take the grating to the photographic plate, lower the dispersion. So he kept it at about 1 inch above so that you can get objective prism spectra. Normally converging beam one doesn't do, but it was good enough and is fairly close enough to the photographic plate. And one of the supernovae I observed with that. So it was the reason I observed with that is that there was a lot of moonlight, and if you observe from here, the moonlight spectrum is also superposed, and that has got the Fraunhofer spectrum, which is difficult to subtract. These days in CCDs, things are easier, but there it was difficult. But if you go to a objective mode, the sky is very wide. It is not through the slit. So it becomes a uniform background with no Fraunhofer lines. So I managed to do that and get this, but converted to intensity because of some improvement made, which you see in the next slide, by one Vishwanath, an electronics engineer. He used an HCL, the company's microcomputer, which we had procured, to control the Carl Zeiss microdensitometer and give us digital output instead of the densitometer tracing. So once you had the digital data, initially uh, I tried use this microcomputer itself to see I could do some reductions on that. It had about 1,000 steps could be accommodated in that. You don't have to go to Fortran and compile and debug and so on. You debug at the lowest level. Whatever you do with hand, you do ask it to do, and the computer would do it. So it was previous one was done like that. Even analysis was done on this, and but subsequently, we had TDC 316, the TDC 316 mini computer in Bangalore. In the next slide. So, so whatever program I started off on this microcomputer, so I ported it to the mini computer in Fortran. And the advantage was you could do much more. You could do Fourier analysis with power spectrum and determine optimal filter for filtering out the background, and such things and things became easier. And whatever programs I could develop at that time, Sunetra Giridhar used them. So she had the data digitized with this microdensitometer for her thesis. So she analyzed with this, and she had her own spectrum synthesis programs running on TDC 316 mini computer, where she did the abundance analysis as well. And the next slide. So by that time, Bapu was not around. In 1982, he has gone to visit European Southern Observatory, and the letters which I received at that time, I thought I'll show you here. So May 27, he said, I am having a delightful time using an optronics microphotometer. I think I do deserve the luxury of it after all these years. See, we are all struggling there. Uh, so Bapu was also struggling with limited funds and trying to get whatever best he can. And we had made some progress later, as I showed you but still it was not nothing compared with this kind of luxury. And but Bapu didn't come back from Germany, though he wrote to me about his uh, plan for open heart surgery, and I look with much optimism to the outcome of it all. But that optimism didn't last. He didn't come back. So then Bhattacharya took over as the next director. So the next slide. So during Bhattacharya's period, I'll show Bhattacharya's picture later, but to continue with the instrumentation and other accessories. So we obtained a new spectrograph made by Zeiss. Ashokpati was the one who was quite instrumental in procurement at that time. Bhattacharya was able to get sufficient funds from Department of Science and Technology. We moved to the Department of Science and Technology. So, so this was a new spectrograph, a professional spectrograph, but initially it had also a Schmidt camera with a photographic plate to be inserted inside. We started getting spectra with that. Later on, adapted a different camera with an image tube, and one of those cameras which we used with the nebulous spectrograph. And then Ashokpati also got a CCD camera, which was used directly as an imager as well as with this spectrograph. But you see, the spectrograph was slender, compact, telescope was small, so we couldn't get as big a camera as required, and we had to use a smaller aperture camera so that it wouldn't introduce flexure. So we couldn't really go as faint as we could have gone with a 1 meter telescope. And Shokpati also procured a PDS microdensitometer. I don't have a comparison between optronics and this PDS, but this was a standard by that time. And so it would give us digital output and fairly accurate if you used slow speeds to digitize. And I just thought that the 1987 I mentioned supernova, Kameshwar Rao coordinated a observatory program with all the 1 meter and 75 centimeter and whatever spectrograph we had were all pressed into it, and so we could present spectra in much better form compared to earlier. So, but all this became possible, as I show in the next slide, is due to Anupama joining me as a PhD student. She came to me initially for a project, and because she was working with Jain on polarimeter, and Jain was going away, and she didn't want to idle during that period. But at that time, then we also began to talk about possibility of PhD thesis, and I suggested the recurrent novae since I had observed U-score P1s, and I told Bhattacharya, who was director, he felt that it is not a viable project because you have to wait a long time for an outburst to occur. But luckily, then same year, RSOFAK had an outburst, and the observations began, and Bhattacharya agreed for the topic, and uh, so from beginning with her thesis, there was a sea change in the kind of papers we are publishing, the log flux and wavelength, and such highly accurate spectra. And this was possible uh, even with photographic plates. See, these were photographic spectra, and you digitize with microdensitometer, somewhere with nebulous spectrograph, and then later on, after the outburst was over, she continued using the UAGS with all its avatars with photographic plate, then image tube, and then CCD, and so on. So the next one shows the further progress. The Tashokpati also was instrumental in getting a VAX 11780 computer for Kavalur. And this computer had it is a mainframe computer, and it had digital command language interface. So you could define your own commands using that. So whatever TDC 316 programs I had, so I could move them there, and uh, for each one give a command like curve fitting, curve and what uh, curve fitting, Gaussian fitting, or spline fitting, and so on, and wavelength scale, and variety of such variety of commands. So we went on developing it as and when whatever we needed for our analysis. So we would develop it. So this software went on improving as we moved to CC domain eventually, and even using Eshel spectra. So this was one paper we wrote initially in the essay bulletin, and we updated this in another paper in the next slide. You see, so here it was the spectroscopy reductions with all the CCD spectra, linear as well as special. Okay, so we'll continue to next slide. So in the meantime, the Venubapu telescope was being installed, and for quite some time we had only the prime focus. We didn't have instrument other than the photographic plate. There was our first CCD was really the one which we used in 40-inch, but then our electronics lab and TIFR Bombay both decided to develop the CCDs for use with this 2.3 meter. This was already declared as national facility. So TIFR people also wanted to use it, and the detector development they also felt they could do and start using it for observations. So, but initially it was only the prime focus CCD was available. So Divakar Maya, my next student, moved from 1 meter to 2.3 meter. He had data from both. You heard him already, but this was only imaging data at that time. And similarly, later on, another student, Mangala Sharma, she also used only the prime focus imaging to do the thesis. We didn't do any spectroscopy. But the first spectrograph we managed to get for this 2.3 meter is there in the next slide. This is Boller and Shiven's spectrograph. which was originally part of image dissector scanner at the Anglo-Australian Observatory, and Pawan Chakrabarti, who later converted it to a spectropolarimeter, he has given the history here. So, around 1985, it was Radhakrishnan, director of Raman Research Institute, who told me the possibility that it will be decommissioned at AAO, and they are looking for someone to host it. And I asked Bhattacharya, and Bhattacharya immediately wrote to Director AAO expressing our interest, and we procured it. Initially, they wanted to give it free, but their board said at least some token money should be paid to show the seriousness of the interest. So we paid something very small amount and managed to get it. But we could never make the image dissector scanner work, particularly because of damage in transit to its control computer, which was PDP-8i. But we waited with the spectrograph. Anupama helped me to even realign it. But the telescope was not yet ready. So when the telescope was secondary was ready in 1989, this went to the 2.3-meter telescope, and the CCD detectors which were developing were the first ones we tried, and later on a photometric off-the-shelf CCD was also procured with full controls and so on, and we used it for some time, but the efficiency was low, and it was good enough for stellar work, bright stars, novae, supernovae, and particularly again the slit its reflectivity was very poor, so it was not easy for us to center anything on that. Even whatever spectra we could have got with a 2.3 meter, we couldn't, because we couldn't easily center it on that. There was no acquisition and guiding system available for 2.3 meter yet. Okay, then we moved on. Okay, and how I should go on quickly. So next, it was when Ramnath Kaushik joined, we proposed that we should get a professional camera for a professional spectrograph for the 2.3 meter as well. And I'd seen one made by Optomechanic Research Inc., a small company for the Beijing Observatory's telescope. And here Ramnath Kaushik agreed. Of course, group committee led by Kameshwara also agreed, and Ramnath Kaushik agreed to fund it, and we went ahead and procured it. And with this, we could start getting spectra of galaxies as well. And next to Swara did some amount of spectroscopy, but her thesis was still heavily based on imaging. And by then, we also moved out to IRAF. So whatever the spectra was software were developed, I didn't feel like continuing, because it was very nice to see that IRAF was also using extremely similar philosophy, but it was developed by a much larger group and continuously updated. Though some people asked me to port my programs to the workstations in Bangalore, I refused. I said that now is the time to move over to IRAF. Okay, in the next slide, I will show you some, okay, just for completeness, I will also show the fiber fed SL spectrograph which Kameshwar Rao developed for the 2.3 meter telescope. And then I will move on to the next slide. To the Himalayan Chandra telescope finally, where I will not talk too much, but I was involved deeply into it further and my Kowloon visits and observations reduced. And here we planned a Himalayan faint objects spectrograph and camera for the main port as the primary instrument. And I should thank KP Singh of TIFR for telling me, give me contact of Per Rasmussen, who was developing such things, and he was willing to develop for other telescopes. And I contacted him, and the next slide shows that the uh, uh, spectrograph and camera, and it is a GRISM-based system. If you remove the GRISM, you can put filters and use it in an imager. And if you introduce GRISMs and a slit, you can use it as spectrograph. And then we also developed an autoguider system. The original autoguider of the 2-meter telescope was not very good. So we got a better one designed according to the way I actually wanted to have it. And the Copenhagen University Observatory built it. With that, it was much easier to get spectra. So the next slide shows my next student, Ramya, started getting spectra of galaxies with exactly knowing correspondence between which spectra for which knots of the galaxy, which star forming region. And next slide shows also the kind of results one could get, putting them in diagnostic diagrams here, and the H alpha equivalent widths plotting. But of course, this and this could be done with uh, the imaging also. The kind of population modeling which Divakar Maya talked about using his own program was later on the Starburst 99 was available through the web interface for us to work on. So there was a sea change in the way we could do astronomy. So particularly with this, I could see that whatever Bapu had dreamed of, so I could finally do, not at one shot, but over such decades. Okay, the next I'll just, to conclude, I'll just show you that other spectrographs which have come up after that. The infrared spectrograph and camera, which TIFR developed T-Respect. I was associated with it, but marginally. And even next one, the HESP in the next slide. So Himalayan, or called Hanley Echelle spectrograph. So this is a high resolution spectrograph with a complete wavelength coverage with no missing portions at the edges like most other Echelle spectrograph used to have. So the time was is very ripe now. And earlier, I would just make a concluding remark that initial days when Bapu used to struggle in Kavalur, and we were all trying the various spectrographs he was building, and we were feeling bad that why can't we have a better spectrograph? I was the one who used to make too many comments about what is wrong with the spectrograph, and he used to sigh. I used to think that he used to be angry with me, but it was the resource constraint is what he was working under. And that letter which he sent me, where the finally luxury he got. So he would have been happy to have the luxury right here if he were here. So with that remark, I thank you for listening to me and close this talk.
Thank you, Professor Prabhu, for a very interesting talk. It was great to hear about how spectroscopy developed over the decades through your personal experiences. Thanks again for a great presentation. I now open the floor for discussions or comments from the participants. Is
Yeah, this
any-
is Annapurni here. Thanks a lot, Prabhu. It was very nice. A lot of things which
Thank
I've
you.
never heard. Yeah, never seen, and those spectra and pictures were there. Thank you.
Actually, I was thinking of you when talking of all those slitless spectra, which you had a new avatar of it later on.
Uh, there is a
The,
message in the chat also that from Sri Kumar.
oh, yeah. Yeah. Thank you, Sri Kumar.
so, so are there any comments or suggestions, or any discussions from anybody?
This is Maheshwar.
Maheshwar, yes.
Yeah, when I was observing with 40-inch, there are many boxes kept in at the observing floor, and I could see many gratings kept inside those boxes. Were they all made at IIA?
No, tell me again, what did you see in the observing floor? Those boxes.
Yeah,
You see the
boxes with
boxes which were there.
yeah,
Box,
gratings.
yeah, boxes which were there, the blue colored boxes, if you
Yes,
saw
yes.
it. Yeah. So they are actually various cameras that we received as a part of the telescope from Zeiss. So I just, the beginning, I just made a list actually. There are many collimators and cameras. So one was F2, another was F6, and then there is a F13 plate holder. So all these were in that, those boxes. Some had collimators, some had cameras, and so on.
Yeah, I thought our MTech students can use those for, playing around with or making some small spectrograph or something like that.
Yeah, I don't know what happened to all others, the spectrograph material. Most often, my feeling is that Bapu used the same components into different spectrographs because he was improvising. So we may not have any older spectrograph around. But these boxes which you mentioned, when last I saw them, there were the glasses were going a bit bad, but they are all really big, nice optics, which probably one can use for some uh, other experiments. They are collimators, but if you are collimators, the cameras are probably used in various places, but there may collimating optics must be there.
Yeah.
Prabhu, there's a question by Shri Kumar.
Yeah.
He says,
Yeah,
was
I
it,
would read it. Yeah.
can you read the chat?
Yeah. Yeah.
Yeah.
Was it usual for Bapu to define a science problem and insist a student pursues it at any cost, as he did to you on spectroscopy of galaxies? Now I'll have to give it a thought because uh, what uh, what I think of Bapu when I recall old things is rediscovering things from what uh, one felt at that time, because uh, Bapu doggedly pursued whatever he wanted to do. That is right, and once he has suggested something, he went on pushing at it. So that thing is right, and uh, so I talked about exactly what happened with me, but I don't have much of experience in such a great detail with others, except say Sunetra's abundance analysis of sea fields, which was also pushing everything to the limit. The TDC 316 was used for doing such kind of spectrum synthesis where which people are doing at much bigger computers, and uh, so that kind of push he always gave. So in a way, okay, maybe I remember also Scarias, where the work on the globular clusters, where he also asked Karia to come to me for some calculations about the sampling error statistics of the central regions, which was particular that needs to be done to do the corrections and so on. So, and incidentally, that was the Skaria and Bapu was one place where Bapu agreed to be co-author. Skaria's thesis paper. Skaria was insistent. Otherwise, Bapu was a co-author only on papers which he initiated and thought of as his interest. For students, when I wrote my thesis paper and I was going to him to show it to him, somebody stopped me on the way and said, "What is this?" and saw the paper. "Why your guide's name is not there?" I went back and retyped with Bapu's name on it and went to him. He looked at the front page, took a red pen and cut off his name. So I said, "You are my supervisor." So he said, "There is a column called acknowledgement." So, uh, so that was also another thing, that though he pushed you at that, so whatever you did was yours. So he thought that whatever you did was yours. He pushed you to do it, but he didn't want to take credit for it. And or nor blame for it. I don't think he liked the last slide which said I didn't publish, trying to get velocity fields by affine geometric transforms. He did not let me publish it, but he didn't tell me to remove it from my thesis.
Professor Prabhu,
Yeah.
there are two comments in the YouTube channel. I would like to read it out. So, Paniveni Udashankar, he says, your talk is very informative. And Professor Kameshwarov says, well done, Prabhu.
Thank
These are
you
the two
to both. Yeah.
comments from
Yeah.
YouTube channels.
My thanks to everybody. I didn't take so many names of people who were around and participate in the development.
So, so if there are no more comments or no more discussions, then we would like to thank again Professor Prabhu for a very interesting talk. And with this, I would like to close today's meeting. Thank you, everybody.